Yeah, sorry. Is now better? Now, in principle, they have the green. That's all that they can do. Okay, so I am going to talk a bit about the QCD Lagrangian. As Professor Guo Fenkun says, I will introduce you chiral symmetry, and I am going to be some technical in chiral symmetry. I mean, my goal is if at the end of the day, at the end of these lectures, you understand chiral symmetry and you can construct some chiral Lagrangians, right? I don't know, perhaps many of you already know about this, and then I am repeating, but then just let me know. So then I will talk about the Wigner-Weil, and the Nambu-Austin realizations of chiral symmetry, and even I will talk about linear and nonlinear sigma models, and then I will introduce the Weinberg-Tomosawa interaction. Why is that? Because, okay, I am going to talk about exotics, and then one of my goals is just to tell you about the lambda 1405. The lambda 1405 is a baryon because I will talk about baryons. And it's an exotic baryon, right? And it's an exotic baryon not because it has quantum numbers which cannot be obtained within the core model. It's just because it's very difficult to accommodate the lambda 1405 in simple core models. And then the lambda 1405 its dynamics, its structure is really linked to chiral symmetry. And then its understanding in terms of chiral symmetry, it was really a revolution, something more than 20 years ago. And then it boosted the field of dynamically generated resonances. So I want you to learn something about the lambda 1405, and then just of some of the partners of the lambda 1405, right? And then I would love to talk also about the lambda C for charm 2595. That it will be the partner, the similar baryon to the lambda 1405, but in the charm sector. Okay? So the first thing that we need to understand what chiral symmetry is to write this QCD Lagrangian. I am not sure, because I think that you have some lectures on lattice QCD. I don't know if in these lectures there was some time devoted to this QCD Lagrangian, or I don't want to repeat myself, but on the other hand, I need to introduce some basic notation, right? So did you get something about QCD Lagrangian, about local gauge transformations, global gauge? So then I will try to go quick about that, right? But then I need to introduce some notation, right? Okay, so the thing is, I guess that someone told you about that, is that in the 60s, it was known that the hadrons, or the lowest line hadrons, could be classified in terms of SU3 multiplets, right? For instance, they could be, for instance, the pions, the kaons, the antikaons, and the eta meson could be just allocated in the 8th representation, representation of the SO3 group, okay? So here you have the pions, here you have the kaons, so you have, so this is an octet, an hexagon, right? So then you have kaons, you have antikaons, and then here you have the pi naught, and you have also the eta, and then this is charge and pi minus. Also, there was well known that some baryons could be classified into a decuplet, okay? The delta decuplet. For instance, there were some baryons that it could be classified according to Here you have delta minus, delta 0, delta plus, delta plus plus. Here you have sigmas. Here you have cascades. And here you have the omega. Sorry? Is this green? I don't know. Can you hear me or not? Okay. Okay, so that was the decoupled representation. Also, you have some baryons, the nucleon and their partners. There was another 8 representation with the nucleons, right? Here you have the neutron and the proton. Here you have the sigmas. Here you have the lambda. And here you have the cascade. This is cascade star. This decoupled was with a spin parity 3½ plus. Here we have a spin parity 1½ minus. So, however, there were no hadrons that could be put in the 3 representation, right? Because in principle, the octet, the decouplet, well, they appear. For instance, if you do 3 star, then you have 8 plus 1. Okay, so these 3 stars, Fenkun, Tolas is something like Q bar 3, in principle 3 star, then you have octets, right? Then you do 3, 3, 3, which that will be 3 Qs. Then you just do the SO3 representation, the reduction of the SO3 representation, and then you get octet, decuplets, etc., etc. But however, there were no hadrons that you could put in the 3 representation, right? So then, when the theoreticians they have a problem, they actually they include a new degree of freedom, right? So they say, okay. Okay, there will be these hadrons, which are quarks, okay, fermions with a spin 1/2, and they say, okay, they will have another quantum number that is called color, okay. And then, for instance, well, I think that this is very famous, right? Because you have, for instance, the delta plus plus, right? The delta plus plus, then if you think that the ground state is S wave, right? And then if you look at the delta plus plus, therefore you have 3 U quarks, and then I am just looking at the larger spin component 3½ so then I assume that all the spins are up, then automatically I have 3 fermions in asymmetric representations, so that violates Fermi statistics, right? So it was very natural to introduce a new degree of freedom that it was color, such that the wave function will be something like 1/√3, and then there will be something like epsilon, alpha, beta, gamma, U alpha spin up, U beta spin up, U gamma spin up, right? So then automatically I have 3 identical fermions, which are in a fully antisymmetric wave function. Okay, but for this you need to have color. So then the thing is, this new degree of freedom, it will, well, maybe I will tell you a few words. So at least you need 3 colors just to make sense of the delta plus plus with spin 3/2. So then the idea is that this color is in a group SO3 of color, and then the magic hypothesis is just to say that the visible hadrons are only in color singlets, right? The visible hadrons are only in color singlets. And then automatically you cannot see a quark because the quark is not in a singlet representation, it's in the 3 representation. So then the thing is that you cannot detect color objects. You can only detect color singlet objects, right? So then in principle, well, if we come back here, but instead of flavor, this 3 is of color, then automatically now you are interested in this singlet. So then just when you just look at mesons, QQR, then you can arrange a color singlet representation is that it will be the color wave functions of the mesons, right? When you do 3 by 3 by 3, but again, no, this 3 is not the flavor, this 3 is in color, then this is 3 by 3 by 3, then you get decuplet, 2 octets, right, 2 octets, and then you get a singlet, okay? So then in principle, you make sense of baryons because there is a singlet representation. I didn't mention, right? But then when I talk about here deltas and nucleons, is if I consider that this is the 3 representation in flavor space, you see that you get decuplets and you get octets, right? But in the colors, I am interested in the flavor representation. Why 3 colors? Well, the delta is an example. I am quite sure that somebody has told you about the ratio. I am not going to repeat because I am not going to repeat because I am quite sure that maybe you have already somebody has told you about this ratio, right? Ratio of the cross section of E plus, E minus going to hadrons divided by the cross section of mu E plus, E minus going to mu plus, mu minus, right? It was Alexandrou, right? This was the Professor Alexandrou told you about this ratio, just to justify that the number of colors is free or not? No? Okay. So then in principle, okay, I will do that. In principle, suppose you have E plus, E minus, you have E plus, you have E minus, here you have a photon, and then you just produce here a Q, and then you just produce here a Q bar. And then something happens here, and this QQ bar, they produce hadrons, right? Okay, so then if you compare E plus, E minus with E plus, E minus, mu plus, mu minus, what is the difference between these two processes? Eh? No, well, there are, very good. The number of colors is one difference, but there is another difference which is here, is the charge, right? Because when you do mu plus, mu minus, when you do E minus, E plus, and here you have a photon, and then you produce here a mu plus, so this is QQ bar. You produce here a mu minus and here a mu plus. Here the charge is 1. Well, here what happens, what appears is the charge of the quark, right? Is that correct? By the way, can anyone tell me why I have chosen mu plus, mu minus instead of E plus, E minus? Think about that. I give you 5 minutes. Do you have the answer? No. Okay. So then in principle, this thing, it will be just proportional to the charge of the, okay, if I have E plus, I minus with an energy where I cannot produce the charge, the charge anti-charge quarks, then this sum runs over the flavors that I can produce, right? So in the case that I can produce only I can produce only the U and the D quark, the sun it will be okay. The U has a charge 2/3 plus charge 1/3. This is the charge of the U quark. This is the charge of the D quark, and then you have what I am doing. Okay, and suppose that I can produce also the U, the D, and the S quark. So then I will have another 1/3 here, and that will be 4, 5, 5, 6, 6/9. So this ratio will be 2/3, right? I am neglecting the electron mass, right? I am neglecting all the masses, right? I am neglecting all the quark masses, and I am assuming that the hadronization always is produced, right? So then what happens is I am just looking the cross section C plus C minus where I produce, where I see the final state up to strange hadrons, right? And then I compare with the E plus E minus going to mu plus mu minus cross section. I heard in the previous, I remember, I remind that the charm quark is of the order of 1.3 GeV, right? So then if I have E plus E minus below 2 GeV or 2.5 GeV, I cannot produce charm hadrons, right? So then you go to the experiment, and then it's not this ratio is not 2/3. Can you guess what is the value of this ratio? It's compatible with 2, right? It's compatible with 2. Why? Because here I should take into account that I can produce the quark with color 1, or the quark with color 2, or the quark with color 3. So this thing is proportional to NC. Okay? What happens if I increase the energy of the incoming electrons, and then I am above the charm threshold? If I am above the charm threshold, then automatically here I can sum another 2/3, right? So then this is now, this 2/3 now becomes 10/9 times NC. And then it's very nice if you just look at any book. Well, this appears in the textbooks. This ratio they jump, and then is really a good indication that the number of colors could be 3. By the way, why has anyone thought about why I am using in the denominator E plus E minus going to mu plus mu minus instead of E plus E minus going to E plus E minus? Because it will be better, right? Because the electrons are lighter than the muons. What is the mass of the muon, by the way? What is the muon mass? 100. But why I am not taking in the denominator E plus? What's your name? Very good. Very good. The thing is that if you have E plus E minus going to mu plus mu minus, this is the only Feynman diagram that you have, which is the same one that you have here in QQ. However, if you have E plus E minus going to E plus E minus, then you may have the T-channel diagram. You may have E plus E minus, and then you have something like that. E plus, photon going to E minus, E minus. Okay, and this diagram is not for Q, for quarks. Then automatically it doesn't work. Tau minus going to hadrons. The tau minus, what is the mass of the tau minus? This electron is, the muon is 100, the tau is 1.7 GeV is almost twice the proton mass, 1.7 GeV. Okay, so then if you look at tau minus hadrons, and then I need always a new tau because I need to conserve electron family, okay? So that will be something like you have tau minus, then you have here the new tau, then you have the W minus, and the W minus can produce E minus, new bar E, or you may have mu minus, and then you have new bar mu, or I can produce D and U quarks, right? Because the W couple not only to electrons, it also couples to quarks, right? It's a little bit more complicated because, well, it couples to, there is a Cabibbo angle there, but I don't want to enter into details. But again, if we look at the width of the, if we look at the width of the tau, then automatically we will see that it will be affected by how many colors are there. You understand? Right? And then just by looking this width, automatically you always get a support for having three colors. There are more technical things about anomalies in the standard model, but I am not going to enter about that, okay? So now QCD. This Lagrangian. So should I go through the derivation of this Lagrangian just very quickly, right? So the idea is that we have three colors. We have chosen the SU3 group. One thing important for choosing because there are other groups where you have the three representation, right? Because I need three colors, then I need the three representation. But the SU3, for instance, I use the SU3. We use the SU3 because in the SU3, the three representation is different to the 3 star, right? And I need that because I could be using something more simple, just like U1 times U1 times U1, right? This is not this group. In this group, what happens is that the three representation will be equal to the 3 star, and this is something that I don't want. Or for instance, I could use the group of rotations in 3 dimensions, right? That also has a 3 representation, but then I want to accommodate that the color degrees of freedom for quark and anti-quarks are different, so I need the 3 and the 3 star different. So then I am left with the color SO3. Okay, so the quarks are fermions. The spin of the quarks is 1/2, right? So then the Lagrangian, the free Lagrangian is something like that. I/2 psi bar gamma mu d mu psi minus I/2 d mu psi bar gamma mu psi. Okay? I am assuming that everybody knows about Dirac fields, and this psi bar is not that I have made a mistake and I have put a bar on top of the psi. It's just that everybody understands this, that this psi bar is just psi daga gamma 0, okay? And gamma are the Dirac matrices. So they are these objects, these objects. Let me just change the notation. Change the notation. That I am not going to do QED, and let me just put Q here, Q, 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 right? And I am going to put here index A, and A is a flavor index. A is flavor, right? So 1 NF, okay? A is flavor index. So this object Q is a is a vector in the Dirac space, so it has 4 components, right? And then it has an index, which is the flavor, okay? And this is the free Lagrangian. I have not put for the time being the mass of the mass of the quark. Yeah, tell me. Well, the difference is just a total derivative, right? And it's for some of the derivations that I am going to do is better. The difference between this and what you are proposing is just a total derivative that I can just throw away through the equation of motion, right? So, but then you will agree with me that the field equations, right, the Lagrangian equations of this Lagrangian gives you the Dirac equation, right, for a free fermion. Okay, so now because I am working with quarks, then I am going to have in mind that the quark field has another index, which is alpha. Alpha is the index of color, right? I am not putting in an explicit manner the Dirac indices, but I am putting the flavor index, that is A, B, C, D in general, and the color index, which are Greek letters, alpha, beta, gamma in general. And this is a field, Q alpha A is a field, so it depends on time and space, okay? Okay, so now I am going to do a color transformation, right? I am going to do a color transformation. Where G is a SU3 matrix in the 3 representation, right? For the flavor index, I mean, for the Lorentz index, is very important if mu is down or up, right? For the flavor index, it doesn't matter, right? It will depend. So then this G is a SU3 transformation in the 3 representations. So this G is a color matrix that, just following my notation, okay? And these lambda A are what? These lambda A are matrices and are the Gelman matrices, right? Because the Gelman matrices provide you the 3 representation of SO3. And the Gelman matrices plays a role, and you will see, in the flavor space, but also plays a role in the color space, right? Because they generate the transformations in the field. This is clear for everyone? And then this little a, I have put many A's here. Right? This A doesn't. It doesn't. This little A runs from one to how much? How many? 8, because there are 8 Gelman matrices, right? In SU2, the Gelman matrices are the Pauli matrices, right? But SU2, I don't want SU2. right? At all. I want SO3 because it's in color, right? This A index here runs from 1 to 8. Okay, if I do this transformation, this Lagrangian is invariant, remains unchanged, as long as G is not a function of X, right? It's a global transformation. If it's a global transformation, this Lagrangian is invariant, right? Why is invariant? Because it's just constructed out of bilinears, right? So here it will appear G, but here in Q bar, because it appears Q daga, then it will appear G daga, and then G daga G equals 1, right? Because SO3 gives you unitarity matrices. That's clear for everyone. Okay, how do we construct the interactions? Just paying attention not to global transformations, but paying attention to what? To local transformations. Fenkun, I need some help. Ah, no, it's here. Okay. Paying attention to local transformations, right? We are going to make this G matrix depend on the space-time. And how do we do that? You see this eta A here. Now, this parameter here, we make it to depend on the space-time. Then automatically, the Lagrangian is not invariant under this local transformation. Why? Why is not going to be invariant? Well, this is the normal derivative, right? It's not going to be invariant just because here we have a derivative, right? Because we are going to have the transform Lagrangian. You are going to have, for instance, in this term, you are going to have something like Q bar, then you have G daga, which is good, then you have gamma mu, but then you have D mu, and here you have G Q. Okay? This is SO3 color, this is Dirac space, I don't care, I can commute, right? So when my transformation was global, then I could take this G daga here with the G, and I was obtaining 1. But the problem now is that I have a derivative. I have the partial mu in between. So then automatically the Lagrangian is not invariant, right? The Lagrangian is not invariant. And to make it, well, just few things because I will need it. I will come back to this just in a minute, right? One thing, well, here I have introduced the Gelman matrices, right? Gelman matrices, which are these lambdas, right? And these TAs, they have something like TA, TB is I, A, F, B, C, TC, right? They follow this commutation relation, right? The F are the structure constants. It's an antisymmetric thing. And then for SO2, this F will be the Levi-Civita tensor, and that's it, right? And then for SO2, lambda will be the polymetrices, and then T will be the spin, right? The total, or the total isospin J, okay? So then here I got a trouble, right? So then, as somebody just mentioned, the idea is, okay, we are going to introduce a covariant derivative. We are going to introduce here a covariant derivative. So this is the normal derivative. These alpha, beta are color indices, right? And then what I do is that I add up, I need to add A new fields, this B mu here, right? And these are going to be the gluon fields. These are going to be the gluon fields. Why do I have 8? Because you now here you have this A. You have here this A index that it runs from 1. It runs from 1. It runs from 1 to 8. And then automatically what I want is, okay, I need to find out how these fields transform under a color transformation, right? And the way that they are going to transform is such that the covariant derivative transform like G d mu G minus 1. Okay? That is going to fix how these gluons, they transform under a color transformation. You understand? Because if I have managed to have this, then automatically, if I replace this normal derivative by the covariant derivative, I am going to have I over 2 Q bar A gamma mu d mu Q A. Okay? Now, if I do a color transformation and then d mu goes to G d mu G minus 1, then automatically, because Q bar goes to G, well, G dagger, G minus 1 and G dagger are the same. G dagger, sorry, Q bar A, G dagger, and then QA goes to G QA, then it works, right? Because I have G dagger G 1, I have G minus 1 G 1, and then automatically I have constructed something that is gauge invariant. Okay? This automatically fixes this requirement here, fixes the transformation of the gauge fields. Okay, so the gauge fields, they should follow this transformation there just to make it invariant. Okay, any question, any doubt about that? Is clear? Okay, next thing, I need to give, because now I have these fields, okay, I have these new fields, these gluon fields, and okay, perhaps what I am going to do is, okay, this B is this field here. This B is a color matrix because it contains the Gell-Mann matrices, right, in the color space. I am going to make explicit this relation, right? I am going to make it explicit, this relation, for you. Okay, so if you just do this, then these fields, the gluons, they will transform like this, okay? Which is just to make explicit this thing, right? I mean, this B here is a matrix in the color space. Here, no, right? Is that clear? Okay, so the difference between QCD and QED is this. Okay, because in QED, in quantum electrodynamics, then you construct a Lagrangian that is invariant under local transformations of U1, which is a symmetric group. But now in QCD, we are constructing a Lagrangian that is invariant under transformations of color SU3, which is a non-abelian. It's a non-abelian group, and then automatically you have these constants here. right? In QED, you don't have this term, and this is this term, this kind of new contributions are those that are going to make more difficult QCD than QED. Okay, so now we need to construct a kinetic term for the gluons, right? We need to construct a kinetic term for the gluons, okay? I think that this is pretty trivial, right? That this is what I should do, right? So I need to construct something that contains gluons. And the important thing is I haven't done it, but what is the virtue of d mu d nu? Is that d mu d nu, okay, if I do a gauge transformation, so this is d mu d nu minus d nu d mu, okay? Now I do a gauge transformation, and then the derivative, the covariant derivative transform like that, right? So then if I do a gauge transformation, I am going to have g d mu g minus 1, then d nu you have g d nu g minus 1, okay? And now I am going to have g d nu g minus 1, g d nu g minus 1. Okay, so that's 1, and then what I have is that this is g d mu d nu g minus 1, right? Now, if I contract the two indices and I take the trace, automatically have something that is automatically I obtain something that is gauge invariant, right? Because if I do f mu nu, then if I do a gauge transformation, then I have that is g f mu nu g minus 1, f mu nu transform with g, f mu nu g minus 1, this is 1, so this is just g f mu nu g minus 1, correct? And then the trace is in which space? In color. Then if I take the trace, the g minus 1 cancels the g, and then I have something that is gauge invariant, okay? That's very easy. Okay, so then what is the difference with QED? In QED, you know that it's just d mu a nu minus d nu a mu, right? Why? Because the photon fields commute. Okay, but now here we have the gluon fields. Our matrices in the gluon space here, right? Then automatically this commutator is not 0, and then automatically is different. Okay, why the minus and why? Well, the minus is irrelevant, right? Because we have FF, so it's just matter of convention. And then why is 1 over 2g squared? It's just because you want to get the Maxwell equation, right? So then automatically you see that everything is fixed, right? And then just because we are using the covariant derivative, then we have the coupling of the gluons to the quark fields, and we have the self-couplings of the gluons. We have 3 gluon vertices, we have 4 gluon vertices, because all of this stuff is contained in the F mu nu, right? Masses, okay? I think that we have here, we have to give a mass to the fermion fields, right? The mass is not a problem for QCD, right? Because you understand that I can, I can add this term without spoiling the invariance and the gauge transformation. Why? Because this is just a bilinear, it's Q bar Q, and there is no derivative in between. So the mass is not really a problem in QCD, right? I am not going to do it because it takes time, and then I prefer to spend time in something else. But in principle, you may start with something more general, something like Q bar A Q B with a matrix, right? With a general matrix, right? You can show that you can diagonalize this matrix always, right? There is no problem, and then, well, this I think that for the discussion here is natural, just that we take this thing, okay? Well, it's up to you. Very fantastic, good, yeah, it's okay. I guess that you heard about that in the previous lecture, no? More or less is clear. So we just resume in 10 minutes. Good. Let me just put this thing just for you. Good. So you are going to see Ulf, right?
Yes, he actually my flight will land in Beijing 1 hour before his, so I will just wait for him in the airport. That's why I will leave.
Okay.
Probably I need to tell the students Thursday morning I would like to take lectures on the first 2 hours, and then the tutorial will be after that, because otherwise I cannot catch up the flight.
No, the thing is that I at some point it was proposed Ulf Meissner
Yeah.
To be member of the scientific committee of IFIC,
Yeah,
right?
yeah,
And this is under discussion, right? And then I thought that because we have this Severo Ochoa program, right?
Yes.
I thought, sorry. Oh,
Stupid question, probably.
yeah.
Here, we've inverted the alpha, beta, the A and the beta upside and outside. It's not a problem. It's like we can
Yeah.
set. Okay, it's not important.
It's not
The
important.
position. Okay.
No, it's not important. I mean,
Yeah,
I mean, the thing is that this acts only on the color space, right?
Yeah,
So
indeed.
then it's a matrix.
Yeah.
So this is a vector. Maybe the thing is that because I know that you have lectures on this last week, I didn't want to enter
okay.
into details, but this is a column. Q is a
No,
column and G is a matrix, right?
No, okay. It's just. I imagine that. So it's just a stupid question to be sure.
Yeah, sure. So the thing that I thought it was a good idea to bring Ulf Meissner.
Yeah.
For a visit,
think so.
because I thought also about you to be member of the scientific committee, so that you will be my proposal in 8 years or something like that, or in 5 or 8 years, right? But at this point, I think with Ulf age and then his prestige in Europe, I think that it was a good thing. And then there is a program of this Severo Ochoa to bring guest professors for stays in IFIC.
Sorry, that's for 1 month.
Well, the minimum is 1 month. I think that they pay something like 2,500 euros or something like that per year, and they take care about the travel, right? And I think that the visit can be split instead of just 1 month, because for a person like Ulf, it's very difficult to stay 1 month.
So,
For a person like Ulf, it's very difficult to stay 1 month
yeah,
in any place, right?
Yes.
So then I thought, okay, perhaps we can split it in 2 weeks,
Yes.
two weeks visits, right?
I think that could be possible because he already decided to come to China for a couple of times, several times already.
For a month or?
No, for 1-2 weeks.
Yes,
The next
and then my idea is, okay, the thing about splitting is, okay, that they are not going to pay two travels, right? But I will pay one, and that's it, right? But then I thought, okay, perhaps it's a good idea in the first visit to bring you also to Valencia, right? And then we could start, begin something
Yes.
together, and then in the second, because you are not going to travel twice to Europe, right? That was the email I sent to you.
Because from the next in the autumn semester, I cannot leave for 2 weeks because I will teach every month
And the autumn semester starts in September,
in September.
at the beginning of September.
Yes.
Okay, so that should be done before that, in June.
If I come to
But
Malaysia for 2
you
weeks,
think
it should be before.
you think it's a good idea?
I think so. Yes,
Just
yes.
to go to stay in Valencia for 2 weeks
Yes.
together, and then
Yeah.
Ulf could come back at some point in September, October again.
Yeah, I think that would be very good.
So then I will write Ulf and I will tell you about
I
that.
already got what days I proposed last time.
Sorry?
The days, I think I.
Okay. So who can tell me about this plot? Okay. I have just introduced the QCD Lagrangian. Just to quantify the QCD Lagrangian is difficult. I mean, because you have, it's not as easy as QED. You have to include Gauss and things like that. And I am not going to enter into details. The normalization of QCD not, but this is important. This alpha is the coupling constant. If you remember in my previous slides, there was a little g, right? That it will play the role of E in QED, and this alpha is G squared over 4 pi or whatever it is, right? So someone aiming just to tell me what this plot means? Yeah, this is the running of the coupling constant. Because when you renormalize then the coupling constant, the strength of the interaction depends on the scale that you are looking at. There appears this parameter that we saw this morning, lambda QCD, that is fundamental. And then if I find, here I have find it. Okay, then we see that a very short distances means large momentum. The coupling constant becomes very small, and then you could understand that the quarks are free, right? That is supported by the partons, right? I mean, someone was working in JLab, right? I mean, Jorken, Andrel, and this kind of physics is just because you could suppose that the interaction of short distances is very weak. But then I have done something. But then a long distances at the hadronic scale, the coupling constant grows and it becomes large, and then you cannot do perturbation theory, right? There is one moment that if you try to split two quarks, a QQ bar is a meson, if you try to split two quarks, from the energy point of view, it's cheaper just to create a QQ bar from the vacuum that keeping putting apart the two quarks, right? Okay, these are the classical equation of motion. This is a nice exercise that you can do it, right? Because I don't know if you have ever done it. Here you have the QCD Lagrangian, then you could apply the Lagrange equations, and then these are the classical QCD equations of motion. I think that there's something that you should do at least once if you want to work in this kind of physics, QCD. Okay, now I go to, I think that I am going to go to the most important part of this first lectures, which are the symmetries of the symmetries of the Lagrangian. And yeah, and there is one theorem which is fundamental, is Netter's theorem, right? Is the first. Is anyone doesn't know anything about the Netter's theorem? You don't know anything about the Netter's theorem. Well, the thing is, when you have a Lagrangian and you have a symmetry of the Lagrangian, right? Asymmetry means that you make a transformation of the Lagrangian and the Lagrangian becomes invariant. Then automatically, what happens is that you can prove in field theory that appears one current, and this current is conserved. Okay, this is the content of Noether's theorem, and this is one of the most important things that this is one of the most important things for the discussion that follows, right? So I am going to write in the blackboard what you can find in this transparency, right? Which is okay. So you just do some transformation. So you have one Lagrangian that it depends on some fields and some derivatives of the fields or whatever it is, and then you make a transformation with some group, right? And then what happens is that your Lagrangian becomes your Lagrangian becomes invariant, right? And then you do automatically, it appears one current G mu, which, well, okay, so it means that if you do an infinitesimal transformation, what happens is that phi prime is 5 plus some variation of the field, right? Plus some variation of the field. This is not totally correct. This is not totally exact because I am just not taking into account transformation that involves the metric, right? I am just doing internal transformation just to make it easier, right? So this is not totally correct. And then because it's conserved means that d mu g mu a is 0, then automatically you can define a charge, right? You just define here a charge, QA, which is just the integral over spatial variables of the 0 component of this current. And then this is conserved. Okay, and this is Emil Noether. It's really very important, Emil Noether. Okay, everybody. Okay, so now we are going to use this thing in my QCD Lagrangian. Okay, the first line. If you look at, you remember my QCD Lagrangian, I am going to make transformation of the fermion fields. I am going to make transformations of the fermion fields. The first one that I am going to look at is a global U1. A global U1. So I am going to do transformations of my fermion fields. Okay. If I do a U1 transformation, es decir, if I change the phase of my fermion field, it's a global. Global means that this parameter here, theta, does not depend on the coordinates, does not depend on the space-time, right? It's a global transformation, and then what I am doing is I am just changing the phase of my fermion fields. The Lagrangian is invariant. It's not invariant? It is invariant, right? Why is invariant? Because it's just a bilinear, it's Q bar Q everywhere. And then because this phase is global, it doesn't depend on the X, then the derivatives do not create any problem, and then my Lagrangian is invariant. And then what I can get the current. right? Because this delta parameter here is just, well, the new field is just 1 minus I theta q, right? So minus I theta q, okay? So this parameter delta here is just minus I theta, okay? So then my current is, okay, is just the parcel of the Lagrangian with respect to d mu psi. Then I have in here, then is you have to sum up the two contributions as you mentioned, but then you just find that the current is just q bar, the current is just q bar A gamma mu QA. Any doubt about that? Because it's just, I take the partial of the Lagrangian with respect, well, in the first, I have two contributions. In first, it is the partial with respect d mu psi, and then I have to add here, which is with respect d mu psi bar. Then you add up those two things, and then any doubt that this is the conserved current? Is there anyone who have any problem? No? Okay. So then I have, this is the conserved current, and then I have a conserved charge. And what is the meaning of this conserved charge? This is the baryon number, right? This is the baryon number, because why is the baryon number? Okay, if you just take gamma mu, you just take gamma 0, then automatically what you have is just q daga q, right? This is the number operator, right? Because q bar is q daga gamma naught. Then if we look at the 0 component of the current, we have q daga gamma naught, gamma naught, gamma naught, gamma naught is 1. Then you have q daga q, this is the number of operators. And I am counting the number of flavors and the number of colors. Okay? So that QCD is telling you that the baryonic number is conserved, right? Now I can do something more sophisticated. Now I can change, okay, it's the second. In the second, what I am doing? I am again changing the phase of the fermion fields. But I am, what is the difference? Is that I am changing in a different manner the phase of each flavor, right? Again, this transformation affects the Lagrangian, or the Lagrangian is invariant. The Lagrangian is invariant under this transformation, right? Why? Because I haven't written here in an explicit manner, but I am summing over flavors. And I am not mixing the flavors. Even in the master, I told you that I was not going to do it because I don't have time, but I can always take a diagonal matrix, right? So what is this second symmetry does for you? It's easy, no, because you just can read it. It's the flavor number conservation. And that's very important that you should bear in mind. Gluons do not change flavor. Gluons do not change flavor. Flavor is changed by the weak interactions. Right? Okay, by the W, by the set boson, etc., etc. Okay, any doubt? Everything comes from QCD. Okay? Next, I am going to find for you isospin symmetry. You have heard about the isospin symmetry many times, and then why isospin symmetry is correct. Okay, now I am going to do something more complicated. Now I am going to do something more complicated. Okay. I am going to pay attention to two flavors, the flavor A and the flavor B. And I am going to assume that the masses of these two flavors, the masses of the quartz of the two flavors are equal, okay? And then what I am going to do is a rotation between these two flavors, okay? What I am going to do is a rotation between these two flavors. So is what is written here, Q prime A alpha is equal to e to the minus I sigma tau over 2 A B Q B alpha. Okay, this is an SU2 matrix. It's an SU2 matrix. Why 2? Because I am considering only two flavors. Does it make sense to you? And that's the reason why it appear the Pauli matrices, because the Pauli matrices generate the representations of the SU2 group. Okay? Just any doubt, this is a column vector in flavor space. This is a 2 by 2 matrix, and this is a column vector in the flavor space. Okay, good. Let's see what happens when we do this. Let's see what happens when we do this rotation. So this is, for instance, to go from the U field to U prime U cos alpha plus D sinus alpha, or from the D to D prime equals to U sin alpha plus D cosinus alpha. You see that I am rotating. I am going from the flavors UD to the flavors U prime D prime, right? Okay, now what happens is that the Lagrangian again becomes invariant. Again becomes invariant as long as the two masses are equal, right? As long as the two masses are, tell me. Sorry? What do you mean a minus? One of these, I don't know. It could be, yeah, thank you. Are you happier? Yeah, it's a rotation, right? It has a minus. Thank you very much. Okay. Okay. So the point here is the following, right? The point is that here in the Lagrangian, I didn't put it, but here I have a sum over A, right? In these terms here, I have a sum over A, okay? But in the masses, in principle, if the mass depends on the flavor, so the flavor A will have mass A, the flavor B will have mass B, okay? So I am doing an SU2 rotation. So then if you look at the kinetic term, it's like computing a scalar product, right? That becomes invariant because I am summing over A, okay? While in the mass term, only if both masses are equal, right? Only both masses are equal, right? Because look at this in the flavor space. Look, Q bar A, QA plus Q bar B, QB In the flavor space, it's something like that. It's a row matrix times a column matrix, right? So then if I do a rotation, it becomes invariant, right? Because you know when you do a rotation, you don't change the scalar product, okay? And this is what happens here with the kinetic term. But here is not true. It will be true only if the two masses are equal. And you remember Fenkun was telling you this morning about exact symmetries like CPT and approximate symmetries, right? This is an approximate symmetry. Why? Because, okay, we may think that the mass of the up quark and the mass of the down quark are more or less equal, but they're not totally equal, right? I mean, the difference that's a question. What is the mass of the up quark? 100 MeV? This is important. I mean, you are doing hadronic physics. Come on. I will help you a little bit. I will mention the mass of the top quark that he didn't mention. The mass of the top quark is 175 GeV. I will go down. The mass of the bottom is 4.5 GeV. The mass of the charge, 1.2, 1.3. The mass of the strange, you want to do hadronic physics, right? The mass of the strange, shall we vote? We are a democracy, right? Any guess for the mass of the strange? Eh? 80 MeV, 78 MeV. The mass of the strange, 80 MeV. I mean, well, here there is a subtlety. Okay, but I don't want to enter into details about because you cannot define the pole mass of the quarks. You can define the current mass that appears here in the Lagrangians. The mass of the down quark, 10. We'll say 10, for instance. Okay, 10 MeV. The mass of the U quark, 3 or 5, okay? But that's important, okay? That's important. That's the reason why he was talking about symmetries in the infinite quark limit, for infinite heavy limit, and symmetries in the light case. But it's not the whole history, right? Because one thing could be large or small, depending. You need to compare with something, right? Because 5 MeV could be very small if I compare with the mass of the top, 175 GeV, or if I compare with the mass of the tau that I told you was 1.73. But it could be very large if I compare with the mass of an electron. So I should compare with what? With the QCD scale, and the QCD scale is lambda QCD. And lambda QCD is the order of 200 MeV, 200, 250, right? So then, just compare with 250, well, the difference between the mass of the U and D quark are negligible, and I can assume that the mass on the U and the D are equal. You understand this point? Then automatically I have a symmetry, an approximate symmetry, because the mass of the U and the D are not totally equal, right? Are not totally equal. And this symmetry is isospin. This symmetry is isospin. And then I think that it will appear, yes, this symmetry is isospin. And, well, I have written here the current, this V that appears here later, but is this. And this is, because I am in SU2, that T is going to be the Pauli matrix, and here you have the algebra of isospin that it will appear later here. So isospin is a consequence of QCD, or let me put it in a different manner. People knew that isospin was a good symmetry, and then the people who construct QCD make sure that QCD was respecting this symmetry, right? What happens if I put the strange into the business? If I consider, okay, I am going to assume that the mass of the up quark, the down quark, and the strain quark, more or less are equal as compared with lambda QCD. Then, instead of isospin, we have what? A sub 3 symmetry. I star, I have already removed erase, right? But I start that I could put an octet of pions that contain the pions, the kaons, the antichaons. I could put an octet with the nucleons, with the sigma baryons, with the lambda baryons. This is a sub 3 symmetry. And this is sub 3 symmetry because then what I do is a rotation not between two flavors, but between the three flavors. And the generator is not going to be the Pauli matrix, it's going to be the Gelman matrix. And in the current, this TA is going to be the Gelman matrix, and that is going to give you the sub 3 algebra. You follow me? Of course, this symmetry is going to be, well, less accurate than the isospin symmetry, right? For instance, what is the mass difference between a neutron and a proton? The mass difference between the neutron and a proton. Yeah, but then if I go to SO3, you remember in the nucleon octet I was putting what? Look at your notes. I was putting neutron and protons in the first line, and the second line I was putting sigma, lambda, and in the third line I was putting cascades, right? The mass of the sigma. (1185), yeah, something like that. The mass of the lambda, 1115. The mass of the cascade. Yeah, you see that the splitting, I mean, in principle, all the baryons in these multiplets should have the same mass, and they don't have the same mass. Why? Because the symmetry, the sub 3 symmetry is less well satisfied, right? Okay, now I am going to do something different, something else. Well, I am going to consider, okay, that's what I have done so far, right? But now I am going to consider also this. That's the reason why then is a composed group. I do an SU rotation, and then also this is a vector SU3 rotation, but I am going to do also an axial rotation here. And why is axial? Because you see, I have put here gamma 5. Up to now, we haven't paid attention to the Dirac indices, right? All of these rotations were in the flavor space. But now I am doing something more difficult, because this rotation in here involves flavor. If I only consider two flavors, that will be a Pauli matrix. If I consider three flavors, it will be a Gelman matrix. But also I consider gamma 5. Okay, so this transformation involves simultaneously flavor and Dirac degrees of freedom, right? Okay, so we can do it in well, we can do it in one of the tutorials, but well, it's easy to show that this is a symmetry as long as all the masses are 0, right? As long as all the masses are 0. Actually, this is the vector current, this is the axial current, and you see that the vector current is conserved all when the two masses are equal, independently if they are different from zero, while the axial current is conserved only when the masses are zero, right? Oh, well, this is fantastic. I have gone very quick. But more or less, you have understood what I am telling you? Okay. So I encourage you to get this vector and axial masses, right? Well, it's easy. It's easy to see it because look at when you have, I am doing something with gamma 5 in the axial, right? When you have something like q bar, gamma mu, I don't care about the d's, right? And q, and I do an axial rotation, right? Then I have something like, I have something like, okay, I do an axial rotation, so then I am going to have q goes to e to the minus theta I ta gamma 5 or something like that, okay? Q. Okay, so then Q dagger goes to Q dagger e to the minus e theta I ta gamma 5 over 2 or whatever it is, right? Q dagger. But then to have Q bar, I need to put a gamma naught, right? Okay, so then Q, so then this is Q dagger. If I put here a gamma naught, here I have a gamma naught, right? But then, if I try to put here, I need to put put together the gamma naught with the Q prime dagger, because in this manner I will get Q prime bar. Then I will have Q prime bar, sorry, Q prime bar, and then a gamma 5 anticommutes with gamma naught. So then I will have e to the I plus e theta ta gamma 5 over 2, right? But now in the kinetic terms, I have a gamma mu, right? Then when I take this is here, then when I commute with the gamma mu to kill the transformation of the Q, then I get again the proper. I have done something wrong. Ah, sorry. It's better if I do carefully. This is wrong because I have done something wrong because this is dagger. Sorry. Okay, suppose that you have Q goes to Q prime, which is e to the minus I theta I ta gamma 5, and then I have put 2. Well, I don't have 2. Okay, forget. I don't have 2. Q. Good. Now, then Q dagger transforms like Q dagger, and then I have to put here plus I theta I ta gamma 5. Okay? But now, if I have Q dagger gamma naught, then what I have is Q dagger e to the I plus theta I ta gamma 5 gamma naught. Then I move the gamma naught here, and then I get Q bar, but it's not free. I should change this sign, e to the minus I theta I ta gamma 5. Okay? Now I consider Q bar gamma mu Q, which is what appears in the kinetic terms, right? In the kinetic terms, I have Q bar gamma mu Q. I don't care about the derivatives. Then if I do this thing, I know that Q bar becomes Q bar e to the a minus theta a ta gamma 5. and I have here gamma mu, and then Q transforms like Q transform here, like e to the minus I theta I TA gamma 5Q, right? But then if I move here with the gamma mu, then what I have is Q bar gamma mu e to the plus, because gamma 5 anticommutes with all the gammas, plus theta I TA gamma 5, and then e to the minus I theta I TA gamma 5 Q. And then this is 1. So then automatically you see that if I do an axial rotation, the Q bar gamma mu Q becomes invariant. I don't care about the derivatives, right? Because the derivatives is a global transformation. However, what happens with the mass term? In the mass term, what you have is just Q bar. Okay, you have Q bar, and then you see that the rotation doesn't cancel, right? And that's the reason why you need that all the masses should be 0 to have the axial current to be conserved, right? Is this clear? Okay. Another nice exercise that we can do in the tutorials on this exercise. Okay, now I can bring in the quantization. If I quantize my theory, I have that the anticommutator of QQ daga equal times is a delta 4, and then automatically you remember all my charges are written in terms of the fermion fields. So then I can get the commutator of the fermion fields. And it can be proved, and we can do one together, is up to you, that the charges that I have defined follow this algebra. And that's the reason why they tell you, okay, the vector current, it follows a SU2 or SU3 algebra, right? In the case of SU2, these constants here become the Levi-Civita. And then automatically what you have is a typical SU2 algebra, okay? If you are in 3 flavors, then you have a SU3 algebra. Now what happens with the anticommutator of the vector and axial? Vector and axial do not commute, right? And then vector and axial, it appears an axial current. Pardon, sorry, an axial charge. Okay, you have vector axial becomes axial. And then when you have axial and axial, this commutator becomes a vector, right? And this is something that it follows directly from our definitions here. Just taking into account that the fermion fields, they follow this commutation, this anticommutation, right? And then you need to sit down, and then automatically you get this algebra. Okay. Here I am talking about in terms of vector and axial transformations, but you probably have heard about left and right transformations, right? Left and right transformations are totally equivalent, right? So the left projector is just 1 minus gamma 5 over 2. The right projector is 1 plus gamma 5 over 2. Then automatically you see that the fermion field Q any fermion field could be written like QL plus Q right, because it's just 1 minus gamma 5 over 2 Q plus 1 plus gamma 5 over 2 Q. The gamma 5 term vanishes, and then you just get Q. Okay? So it's just the transformation, the vector axial transformation, this vector axial transformation, which is just SU left cross SU right. This is equivalent to say, okay, what I am going to do is I am going to change the phase of the left component of the fermion field independently of the phase of the right component of the fermion field. Actually, you can, which is just this transformation here, right? I just rotate the left components of the fermion fields or the right components of the fermion fields. And then you see that the left current is just V minus A, and the right current is just B plus A, okay? Then you come here, and then what you find is that left closest group gives you an algebra of the group, because left gives you left, okay? Right gives you right, and then left and right commute. And this is the current algebra of the cystis, right? This is another very interesting exercise, okay? You could take the axial current, and this is very interesting with the Nambu-Goldstone and the spontaneous symmetry breaking. You can just compute the commutator of the axial charge and the pseudoscalar operator, and then you just follow all the commutation of the fermion fields, and then you just find that this is just minus 2/3. The minus 2/3 is irrelevant, but the important thing is that it's just Q cube R Q. It's the sum of Q cube R Q. Okay, so nothing. Up to now, nothing. Okay, now there is something that is very important, which is the following, which is the key point. You have a symmetry in the Lagrangian. You have a symmetry in the Lagrangian. Okay, so this is quantum mechanics, which is very easy. Okay, suppose that you have some symmetry, U. Yeah, it's a symmetry of your dynamics because you have that your Hamiltonian commutes with these transformations, right? Your Hamiltonian commutes with these transformations. And suppose that you have a state A, and then you transform with this symmetry the state A into a state B. Okay? Now I compute the energy of the state A. This is just A, H0, A. Okay? And let me write this thing like A, U daga U, H, U daga U, A. Now I take U daga here. I take into account that the H0 has the symmetry. Then automatically what I have is U acting over A is the B state. So I have B, H0, B. Right? Okay, this is the reason why you have the pions. You have here pi plus, you have here pi 0, you have pi minus. You could consider that the mass of the pi minus is equal to the mass of the pi 0 is equal to the mass of the pi plus, because I have a SU2 symmetry and I can move from the pi minus to the pi 0 to the pi plus. In the case of SU2. In the case, if I have also the kaons and I have the anti-kaons here, right? Just in a SU3 symmetry of flavor, then in principle, using this kind of arguments, well, the mass of the kaon should be equal more or less to the mass of the pion, and so on and so forth, okay? Because it's just this thing. Okay, all of these measures, they have spin parity 0 minus, okay? They have spin parity 0 minus. For instance, also, there is another octet which is the octet of the vectors. Where I have the rho 0, here I have the rho plus, here I have the rho, here I will have the K star, here I will have the anti-K star, and here I will have the omega. The mass of the rho is 770, the mass of the K star and the K bar star is 892, and the mass of the omega is 770. So you see that more or less this is another octet, and the spin parity of these mesons is 1 minus. Okay, so then in principle I can move in the isospin line, and I can say, okay, the mass of the rho is independent of the charge. If I use SU3, I can move from the rho to the K stars, and more or less it works. Okay, so that means that the vector part of the symmetry works. However, in principle, if I have also axial symmetry, I should be able to find particles more or less with the same mass as the pions or as the kaons, but with parity plus. And then also, I should be able to find axial vectors. I should be able to find also vectors with parity plus, spin 1, more or less with the same mass of the rho and the K star. You understand this thing? Because this easy. This is what is called a Wigner-Weil realization of the symmetry. If we go to the Hadron spectrum, we find that, okay, the vector part of the symmetry more or less works in this manner, but however, the axial part doesn't work. So there is something that we are doing, that we are assuming that is not correct, okay? And what we are assuming that is not correct in the case of the axial is that the vacuum does not respect the symmetry. The vacuum does not respect the symmetry, okay? And here is where it comes the concept of a spontaneous broken symmetry, right? So then in QCD, what happens is that the vector current is realized at a Wigner-Weil. However, the axial is not being realized at the Wigner-Weil, right? Because we don't have multiplets, right? Because you see here, when we say that UA here, when we say the UA is B, so what we are assuming is the following. And then I think that after this, it will be a good time to finish the lecture today. Okay, so this is the vacuum. Then you will have a field, right? That it creates the particle. Okay? Now, the B, it will be another field that acting on the vacuum, it will create the particle, right? Okay, so now when we compute UA, what we have is U, we have phi A vacuum, okay? And then what we say is, okay, this can be written like U5A, U daga, U vacuum, right? Now, we assume that this becomes the field B. But to have the things work, I need to say that U acting on the vacuum is the vacuum, right? Then you see here, I need to assume that U acting on the vacuum is again the vacuum. You understand? Okay, U is going to be something e to the minus Q, A something, right? Some charge, the charge associated to the symmetry, right? Okay, so then if the charge annihilates the vacuum, it works. If the charge does not annihilate the vacuum, it doesn't work. And that's what is happening with the axial. Have you understood the point? Eh? So here when we say UA is B in quantum field theory, what you say is, okay, you have your transformation. The state A is some field acting on the vacuum. Okay, then you say U phi A, and then you insert here U dagger U. And then this relation, when you say UA is B, in principle, what it means is that U, the transformation of the field A is the field B. But then you have phi B, U 0. If U acting on the vacuum, if U acting on the vacuum is the vacuum, everything works. But if U acting on the vacuum is not the vacuum, then it doesn't work. And then it's related with the charge that is generating the transformation, right? So then, in principle, the axial current is something QCD is more complicated in the axial sector, and the axial current is not going. So this is only possible because the QCD vacuum is not only perturbation theory, right? Because in perturbation theory, all the operators annihilate the vacuum. So the point is that the vacuum of QCD is very complicated, and the axial current is not going to annihilate the QCD vacuum. Okay, and I think that is good time to finish, and I hope that more or less you have understood the things. Okay, tomorrow, well, in the following lectures, I mean, I don't have people helping me, right? So then in the tutorials, we could just do any exercise, or we could just discuss things. It's up to you, right? Because I cannot do all the things on the blackboard, okay? There are, for instance, these commutations of the charges. I think it's very interesting just to do once in life, just to see that everything works, okay? Okay.